So I thought I'd start it off just by asking a broad question of our speakers, because we heard about a lot of pretty interesting discoveries that were made in these different areas. And I thought, considering the conversations we had yesterday and how worried we were about data not being really usable and not being shareable in a way that anyone could really do anything with it, I was wondering if the speakers could tell us a little bit about what, with the data that they've either produced or shared, or reused, what were factors that made it so readily reusable for your work, or that you think make it really useful for the community, or factors that didn't? If anyone wants to chime in.
Well,
Yeah.
I mean, I can start, but because okay, this is on. So we put all of our data on. We put all our code on GitHub and the data on Data Triad. So I'm not sure if that answers the question, but.
Yeah, or maybe those who have sort of worked with data that's been reused by other groups or that they've reused. Mackenzie, for example, I think.
Yeah, definitely. Yeah, so I think it was also discussed a bit yesterday, so thanks for bringing up that there's also a lot of data repositories. So it's not always clear where to look for data and what's the best source. And so I kind of mentioned a few that weren't mentioned yesterday, like Hugging Face for machine learning models, because even sharing model weights is really important, right, and things like that to use this. But I think it all comes down to metadata, which we discussed. So knowing what exactly is in the data to reuse it, I think that's really critical for us to be able to reuse it. And yeah, kind of in a nice way, any of the data sets we use, we never contacted the authors we never needed to contact any of the authors of these data sets to actually use the data. So we only wrote to them afterwards to be like, hey, hope this is great, like maybe of interest. But I think that was a testament of actually like really good metadata that we didn't need to do that, so. Yeah.
Okay, yeah. I will open the floor for other questions. Sure, go ahead.
Kind of going back to yesterday, my question about models, and coming back today to compression. Majority of the models which you talked about, the manifold, okay, McKinsey pointed out the non-linearities, right? They're important to capture more of their, but if we talk to Thomas Serra, he is also making accent on recurrent models, right? So if we're talking inhibitory, excitatory networks, we need this kind of dynamics, right, and consider time. Where do you see field going in terms of exploring more of these dynamic models and reaching even more kind of explainability of what we're dealing with, and maybe compression ratios, which is what's important for us for data?
So this is a small diversion, but I love dynamical systems. In fact, the dynamical system is the reason that I got into neuroscience in the first place. Before that, I was doing microbiology, and there just wasn't enough math. And so the reason I like it is because I feel like what is biology except the spectacular ability of animals to change in time, right? So this is the natural language of describing brain and behavior, and it's something that is really delightful to see the community really embracing in many different ways. As you correctly pointed out, like if you talk to anyone who works on the applied math and does dynamical system control theory, just start listing the things that are difficult to make a system, right? So things that are nonlinear, non-stationary. It just keeps going, right? And the biology has every single one of them. And so we're really pushing the front of what is capable, the capabilities of these methods to describe the systems that we have. And I think that's actually really one of the really great opportunities of our field. Math historically has been driven by need, right? By physical and biological examples, wanting, like pushing the boundaries of what was possible by the methods. So there's a lot of history of that. So I think one of the more exciting things in my mind going forward is really looking at what we observe in biological and neural data and seeing what new mathematics we need to develop in order to understand it. Because I think the frameworks that we have right now, I mean, I work with a lot of physical scientists and engineers and mathematicians of different stripes, and when I describe the systems that we have, like they start tearing their hair out. It's like, wow, like, you know, you thought turbulence was hard. The brain is harder, right? And so we need to develop new methods here. But I think what we cannot throw away is our intuition and expertise as scientists So what I don't like is people who say, oh, let's just throw all of that expertise out the window. People who have been doing this for decades and have a lot of intuition, have a lot of expertise. Let's not throw that out the window. We can actually build models, even machine learning models that incorporate that expertise and have the scientists' intuitions baked in. I think that's something that is going to be really necessary here. Something Andreas talked about is this idea of digital twins. Which is the terminology that people use in engineering all the time, right? If you build a digital twin of an airplane, it has this systems engineering aspect to it. We're really talking about separate models of lots and lots of bits and pieces of the airplane actually put together in a way that runs, right? Like generates new behavior, interacts with the physics of the world, for example, actually generates thrust and has drag and actually flies, right? And I think that's one of the areas where I think we need to go to extend this digital twins analogy, right? The brain fundamentally evolved, the nervous system evolved to move animals in the world. This is what we do, right? It pushes on the world and the world pushes back. And that's an aspect of modeling and really embracing methods from dynamical system control theory that I think we should go in as a field, because I see the brain and the body as being inseparable. And so that's something that I would like to see us model more going future.
Okay. Does this work?
Yes.
Yeah. As a biologist, I have heard several people say we need to find new math. I've even heard Roger Penrose say that. What do you precisely mean by that? Where is this domain of new math coming from?
So they're not necessarily brand new pieces of math, but it's more like, when I took my first class in differential equations, right? I love differential equations, but the class was all about analytic solutions to the small subset of solutions for which we can actually solve. Like, that's not the dynamical systems that's actually used for biology, right? We want numerical methods and things that are actually stable and are flexible enough to deal with complexities of the real world. So for example, a lot of people, like linear dynamical systems are awesome because they're just unreasonably good at actually modeling things, right? We know they're not true, but they're really good at modeling different things. And so people would build stuff on top of it, like what if it's a linear dynamical systems model, but it actually switches, right? That allows us to capture more things. What if it's linear but slightly nonlinear? What if it's a superposition of slightly nonlinear dynamical systems? How do we infer that back from data? That's sort of the kind of math I'm talking about, right? Like writing down the formalism or what we think are true of the underlying system, and then actually developing new methods to infer that from the data. And McKinsey's talked about SIBRA as a really beautiful example of an attempt of something like that we're doing, right? And so math is not, in my mind, exclusive of the kind of math I like is numerical methods, right? Because like data is all we have. Data is what we have about the world. I'm not really interested in analytical abstractions that don't have any bearing on reality. And so data is what we have, and actually inferring what happens in the formalism from the data, that's the piece of math that people in kind of numerical methods have been developing, and I think that's the piece of it that we really need. So it's not like, like abstract math is there's a quote that I like from Tom Stoppard, Berkeley, right, from Arcadia, and about how abstract math used to be really weird, right? It kind of left the real world behind. But the freaky stuff is turning out to be the mathematics of the real world. And in Penrose's work is an example of that, right? Like just looking around, you see inspiration from nature, and I personally find a lot of inspiration from nature. And the need to actually understand the complexity of the world is something that I think will inspire new math. There's examples, but I don't know if that was too abstract.
Thank you. Perfect.
I think we have time for one more intervention. Yes, go ahead. Oh, sorry. Yeah, I didn't point clearly. Sorry. Go ahead, in green.
Yeah. I mean, to ask though, doesn't true conceptual insight come from analytically solvable approximations? Because very often we understand a system where we can actually solve the math, not just in a numerical sense, because that's something very black boxy, but when we can show where the emergent phenomena don't happen magically, but are very rooted in something that we can mentally comprehend.
I would contend that the limitation there is our own, right? Like what we can actually solve is dependent on the tools that we have. And I feel like if I can have the assistance
solved a problem, that has to be good enough for me, right? I think we move beyond that, but I do believe in formalism, and I believe in moving back and forth between numerical methods and analytic understanding. But the class of equations we can actually solve is just too small. I don't think we can break down an equation for the brain. People have tried, right? Lots and lots of people have tried. It just doesn't work. And if that's our definition of understanding, I'm personally not on that path.
I think maybe what you mean is like a normative understanding. I mean,
Yes,
it's
yeah,
not about the
yeah,
math,
yeah.
it's more about, it's the math in the end, but it's like you can have a theory that you can write down some toy example, but then, I think you're right, like it doesn't mean that, but that can like make predictions and then you won't be able to, so then you can come with like numerical approximations to prove it, like, things like, there are theories out there about the brain that maybe you cannot quite write mathematically, but can inspire sort of trying to find numerical approximations. Because I think ultimately I agree. I think it has to be cannot just be like, and that's the problem with machine learning. Now, it's a taste thing. For me, I like simple things. At the end of the day, I think it would be very disappointing if the brain is just like bunch of stuff that sort of is, we can make predictions, but we don't have like simplicity. But I think a little bit is a bit taste. That's why like biology sounds very messy, and but it may not turn out like that, right? Like for example, genes. Like why do all these genes? It's like, okay, you go to molecular biology talk, it's like, okay, there's this cancer gene and that, and it's like, okay, there's no principles, and that's kind of a little bit. But some people like that, so I think it's a bit of a taste.
There's some principles. They're like transfer.
There are genes, the double cube.
Every single one, right? Like,
Yeah.
It's biology. Of course.
We might have to make do with some mess.
Like the double helix is a beautiful structure. I think it has to do with like looking for beauty in data somehow, and symmetry.
Yeah.